All right, this video is for AP Calculus, and this is the second video in a series on limits and continuity. This one, we're going to talk about finding limits analytically, which is our main method for evaluating, especially when we don't have a calculator, which we don't have a calculator on 2/3 of the AP exam. So yesterday we introduced the idea of what a limit is and what would make it exist. Not all limits exist at all x values. Right? So that's important to know. Anytime you have, for a limit to exist, you have to have the same y value being approached as you approach x. Let's just review quickly. If you have a target x value c, and you approach from the left, and you approach from the right, so you're approaching from the left and approaching from the right, if the y value is approaching some number, and the y value on this side is approaching some number, and those are both numbers, and they're both equal, you can declare that the limit as x approaches c of that f of x is equal to that target value that's being approached. All right, and yesterday we focused on numerical and graphical. Numerical is when you plug numbers in, getting close to the target number from below and above. That's easiest to do with a calculator, or graphically, which is easiest if a graph is provided in problems. Sometimes you can just visually see what is being approached. Right, but when we don't have a calculator, we can do this third method, which is called analytically. So to explore that, we're actually going to break this lesson 1.2 here in the number and sequence into two videos, because there's that kind of basic part of it, and then there's some add-ons. So I think it'd be easier if we cover this in two versions. Let's do this. We can evaluate this limit here numerically or graphically. Could we do it in some faster way? Okay. Now we already know. Let's just review how to do this numerically. Okay. So if I did this the way we normally would do it, we would say the limit as x approaches 3 from the left of x squared minus 25 over x minus 5. Right. And I could do that with the calculator. That's what we've been doing. So I could plug this function in as if I was graphing it, which would be x squared minus 25 divided by x minus 5. And then I could use a table, and I could plug in numbers like 2.9, 2.99, 2.999, and I would get numbers getting closer and closer to 8, so I could declare that this is 8. And I could do the same thing in the calculator with values coming down from the top of 3, like 3.1, 3.01, 3.001, and we would also get that same number 8, which means, therefore, the limit as x approaches 3, without specifying the direction of x squared minus 25 over x minus 5 is indeed 8. And that's the correct answer. Okay. Is there a faster way to get that, though? Why is it that if we approach from the left and from the right, we still get the same number? So if I were to graph this function, actually, let's try something here. If I actually plug 3 into the function, then it seems like I can get the number 8. That's weird. You know, before we said sometimes you couldn't plug the number in because the situation's undefined. But in this case, I could literally try plugging the 3 into the function, and I would get the same 8 that's being approached if I'm coming down from the upper part, 3.1, 3.01, 3.001. Right? See how these are approaching 8, right? But in this case, I could have just plugged the 3 itself in. Now, it's really important to know this, that what we're going to do when we evaluate analytically is we're going to go ahead and attempt to just plug in the target x value. But we're not really plugging it in. We're just trying to more quickly figure out what value is being approached as we get close to, but not at 3. But for the purposes of evaluating the limit, you can simply try plugging this number in. Right now, when we do that, we're going to go ahead and say, we're not going to write the limit again, because now I'm actually like on this side. I'm starting to evaluate this number. So now that I'm going to plug this number in, I'm just going to show that's 3 squared minus 25 over 3 minus 5. We can just try plugging this in. That's 9 minus 25 over negative 2, which is negative 16 over negative 2, which sure enough is 8. And that means we can just say, therefore, the limit as x approaches 3 of x squared minus 25 over x minus 5 is 8. Right, so evaluating analytically, when we do this, we're doing what we call evaluating a limit analytically. We attempt to analyze what's happening in the vicinity of the target x by literally plugging the target x into the function. Because if the function is well behaved, that means that we're going to get the same thing. Now let me actually graph this function since we have it in the calculator. Right, as we approach 3, sure enough, this is just the equation of a line. So it's nice and well behaved in the vicinity of x is 3. There's no asymptotes or weird things going on. And so yeah, so we can plug the value in there. That's perfect. All right, so let's try another limit. Same function, but this time approaching x approaches 5. Okay, let me show you something on the calculator. If I were to go to the table, and I'm going to approach some numbers below, and then at 5, and then above 5. So let's say that I was at 4.9. I'm coming up to 5, 4.99, 4.999, and then I'm going to try to plug the 5 in, and then 5.001, 5.01, 5.1. Okay, so as we approach from the bottom side here, these y values are getting close to 10. As we approach from the upper side, they're coming down close to 10. But when we plug the 5 in, we get an error. And that's because if you look at the function here, if we plug a 5 in right now, we're getting a divide by 0 situation. And we know that that is undefined, right? So we cannot, in this case, although we could plug a 3 in there, we cannot plug the target value of 5 in there. Right? And yet, it does still seem like this is approaching a certain value. In this case, it's 10. Right? So rather than go and officially plug in numbers below and above, could I do something so that I can successfully plug the 5 in? And maybe you've already noticed that this function is factorable. Right? If you draw the graph of this function, it looks like a straight line. Now, let me show you on the calculator here. If I zoom out here a little bit to higher y values so we can see this better. If you graph this function, it is the equation of a line, and even out here at x is 5, it looks like it's just going through there. The calculator will not draw the little circle here, but technically there's a hole in this graph right at x is 5, because you can't plug 5 in, but it does seem like it's well behaved in that region. Why does the graph of this crazy function here look like a line? Well, the reason is because you can factor the numerator here. X squared minus 25 is the difference of squares, so that can be factored into x minus 5 times x plus 5, and then you can factor out an x minus 5 and cancel those by making them the fraction 1 and removing them. And this is algebraically equivalent to the equation, or the expression x plus 5. And that's just the equation of a line. Right? So here's the way we would do this. If you have the limit as x approaches 5 of x squared minus 25 over x minus 5, you can mentally kind of plug that in and say, oh, that's a divide by 0, which means that's not going to work. Then you can say this is equal to the limit as x approaches 5 of, and show this factoring, x minus 5 over x plus 5, right, divided by x minus 5. And if I factor that out, I'm left with a 1 here. These cancel because it forms a 1. That's equal to the limit as x approaches 5 of just the x plus 5. And then we said we can try to plug the target value in. Now, if I do that, if I plug a 5 in here, I'm just going to say equal to 5 plus 5, which is 10. Therefore, the limit as x approaches 5 of x squared minus 25 over x minus 5 is simply equal to 10. And the theory behind that is, if this expression is algebraically equivalent to that expression, it has to have the same graph shape, except potentially a hole at the target x value. And that means if you can safely plug into this function, you are finding the y value that's being approached in the original function. And therefore, you don't have to explicitly check on the left and the right. In this case, where you have a single rule, you can attempt to do this. Now, this is important. You should only do analytical evaluation with a single rule. Okay. If you have a two-sided limit, then you have to, well, you can use analytical evaluation for each one, but you have to check each rule on the left and the right-hand side. And we'll take a look at an example of that in a second. Okay. So that's the idea. If you can simplify algebraically, then you can plug in the target value to see what's being approached. Okay, here's another example. Limit as x approaches 0 of f of 2x and then x squared plus 4x. Rather than explicitly checking this, I'm just plugging this 0 in and I'm noticing I'm about to divide by 0. So I'm going to say limit as x approaches 0. I can factor out an x on the top and an x on the bottom, leaving an x plus 4. This x over x is a 1, so it can be removed. So that's equal to the limit as x approaches 0 of 2 over x plus 4, which is the same graph shape as the original function. Now I'm going to plug the 0 in here, 2 over 0 plus 4, and that's 2 over 4, or 1/2. Okay, so this limit evaluates to 1/2. We never had to plug numbers in. Other than the single target value, you didn't have to plug with a calculator numbers, decimal numbers getting close to 0 above and below. Okay, a couple of things about notation I want to point out on this, because notation is really important here. I have to still write this limit notation while I'm in the process of simplifying, because I haven't evaluated yet, right? You've got this is the structure, limit as x approaches c of some representation of a function equals the limit number, right? So while you're still working with evaluating this, you have not yet taken the limit. You're still working on this side. But once we plug the target value in, we have now transitioned to this side, which means for this step, there's no limit, right? Here, this is now, we're saying this limit is equal to some number, and these values over here are just values of the number. So it's important to include the limit, include the expression for the function while you're working on the left side. And then when you finally get to a step where you're transitioned to the right side, then you don't include the limit anymore. All right? All right. Before we do this next part, I want to show one more example problem from the previous notes. Okay, I want to just make a, let's see, do I have that? I'm just gonna do an example here. Okay, we had a problem in the last video that was something like this. F of x was defined as a piecewise function. So let me do this. Let's define f of x as the rule 3x minus 1 whenever x is less than 1. Maybe it's 5 whenever x is equal to 1, and it's 3x whenever x is greater than 1. Now in this case, we don't have a single rule, okay? Which means we do definitely have to check on the left and the right. If we're trying to evaluate what is the limit as x approaches 1 of f of x. Okay, so we're going to check from the left, limit as x approaches 1 from the left. And the reason I'm explicitly going to check from the left is because I have different rules which might apply in different parts of the domain. So that limit of f of x is, now I'm going to write this limit over again, but I'm going to go ahead and replace this f of x with the rule that applies just to the left of 1, which is this rule here, 3x minus 1. Okay, but when we get to this step, in the last lesson, we did the thing with the table, and we plug numbers in here coming up from below 1. Now I'm saying we can use analytical techniques to evaluate by trying to plug the 1 in here. So that would be 3 times 1 minus 1, which is 2. So the left-handed limit approaches a 2. Okay? So you can use an analytical approach, but you have to use that on separate rules on the left and the right, if there are separate rules. In this case, we have the same rule that applies everywhere, so therefore it by definition applies to the left and the right of 0. But here we have a different rule on the left of 1 and on the right of 1, so we have to still go back and do the limit as x approaches 1 particular direction. So this is 1 from the right. Okay, so if we're having a limit as x approaches 1 from the right of f of x, that is equal to the limit as x approaches 1 from the right of, now just to the right of 1, x is greater than 1, so the rule changes to 3x. And then when I evaluate analytically, I will put just a 1 in there, 3 times 1, and that's equal to 3. So what we're saying is, as we approach 1 from the left, right, this function is approaching a 2. As we're approaching x is approaching 1 from the right, the function is approaching 3. And since those two things are not matching up, we have to therefore declare that the limit as x approaches 1 of f of x does not exist, because there's not a single y value. right? So you can plug in, but if you have separate rules on the left and right, you should do that separately on each side. And you can, even though we're approaching from the left and right, you still approach the target value of 1. So you plug the value of 1 into each of the rules. Okay, so many of these limit examples have been of what we call rational functions, which means the functions that are in the form of a fraction. So it is helpful to think about what can happen when you plug in a target value to a function. There's really only some general cases, and we should include some cases actually where x is approaching an infinity. So this number here, we can approach either infinity or negative infinity as well. Um, so we'll talk about that in a second. Okay, so uh, let's look at all the cases here. And actually, before we do that, a note about infinities. Let me add on another thing here. If we have a number like limit as x approaches 4, right, we can approach that 4 from below or from above. X can approach 4 from the left, or x can approach 4 from the right. So it makes sense to split that up that way of some function, right? But let's say that you don't want to have a number. What if you just want to approach infinity? You just want to make x get really large, right? Well, that means we could write limit as x approaches infinity, but it can only approach from the left. There's no way to ever approach infinity from the right because it's not a number. So although technically, I guess you could write limit as x approaches infinity from the left, you should never write the limit as x approaches infinity from the right because that's impossible. In fact, we don't even use this notation. We just say limit as x approaches infinity if we're approaching an infinity. And likewise, if we're supposed to be approaching negative infinity, making x get really large in that direction, right, we would write limit as x approaches negative infinity. We wouldn't write things like limit as x approaches negative infinity from the right, although technically that is correct. And we definitely wouldn't write this, limit as x approaches negative infinity from the left. Right, so don't write those things, just limit as x approaches negative infinity. Right, we'll have a whole lesson just on what happens when we approach infinity. It's either in the x or the y. But since we're going to talk about them briefly here, I thought we should talk about that notation thing. Okay, so what happens when you plug in a target value to a function in the form of a fraction? Well, if you have an example like this, let's say limit as x approaches 3 of x plus 3 over x minus 1, and you plug in the 3 here and here, you get 6 over 3. You just get a number over a number. So that's definitely a possibility, right? Very common. You can get a number over a number. And if you do, it's simply equal to whatever that number is. Okay? When you do that, you could get, when you plug in x in here, a 0 over 2. So I just want to emphasize that 0 over any number other than 0 is simply equal to 0. That's, you have a pie. You divide it into 2 pieces and you take none of the pieces, so you got none of the pie. So 0 on the top of the fraction is perfectly fine as long as it's 0 over a non-zero number that's equal to a 0. Okay. But what if you have this? Let's say I limit as x approaches 1 of x squared plus 2x minus 3 over 2x minus 2, right? That does factor, actually. If we try to plug a 1 in here, then the denominator would be 2 times 1 minus 2, which is divided by 0. So we could try our factoring approach, right? The top would factor into x plus 3 times x minus 1, and the bottom would factor into 2 times x minus 1. The x minus 1s would cancel, so that means this is algebraically equivalent to x plus 3 over 2, and now you can successfully plug in the x here, and you get 4 over 2, which is 2. Right, so when we first tried to plug this in, and we've got a divide by 0 situation, we should also look at what happens when we plug in on the top. Because when we plug in the top here, we have 1 plus 2, which is 3 minus 3 is 0. So we actually have a 0 over a 0, okay? Instead of a 0 over a number. Now, whenever we have a 0 over 0, that has a specific name that we're going to talk about more later in the course. It's called an indeterminate form. And the reason why is because it can resolve to different sorts of structures. In this case, this limit resolves to a number over a number, and therefore resolves to a number. So an indeterminate form of 0 over 0 could become a number, right? And trying to factor or algebraically change the structure so you can plug in is the way to figure out that number. Okay. Now let's say we have this case where we said we're going to have limit as x approaches an infinity. Let's say the function was x squared over x cubed. Well, if you were to plug that in right now, you'd have infinity cubed, or really not, you can't plug infinity, but like a giant number squared over a giant number cubed, which is a giant number over a giant number. So that's an infinity over an infinity. And that's also an indeterminate form. Again, we'll talk about this more later. Indeterminate form. But what we can do is try our factoring thing, right? So if you get infinities instead of a 0 in the denominator, you can also try factoring. So if I factor in x squared out of the top and the bottom and cancel that, this is algebraic equivalent to 1 over x. And that means it simplifies to a number divided by something which is going to infinity, right? And if that's true, if you have a number like, let's say 5 divided by 1, that's 5, right? But 5 divided by 10 is a half. 5 divided by 100 is like 0.05. 5 divided by 1,000 is 0.005. And this is very rapidly going off to a 0, right? So a number divided by something going to infinity is approaching 0. So you can just declare that that limit is equal to 0. Right? So just think about what happens if you have a constant divided by a large number. That is going to 0 as this bottom is going to infinity. Right? Now, what if the situation was reversed? What if we said limit as x approaches infinity of x cubed over x squared? Well, that's an infinity over infinity, so it's an indeterminate form. But if you factor an x squared out, now you're left with the limit as x approaches infinity of x over 1, which means that's a giant number divided by 1, which means it's just going off to an infinity and therefore does not exist. Right? So that's why this is called an indeterminate form. This could resolve to a number, it could resolve to a 0, or it could resolve to an infinity. Okay? And the last case here is if you have limit as x approaches infinity of, say, 3x cubed, 4x cubed. If you factor out the x cubed, then you just get a constant. Limit as x approaches infinity of 3/4. There's no place to plug in the x, so it's simply equal to 3/4. And that means that infinity over infinity could be a number over a number, which is simply a number. Okay, so how can you detect these? Just as a preview, we're going to talk about more later in the following section. But if you specifically have x approaching infinity, if you have polynomials and the degree on the bottom is higher, then that means this is going to approach 0. It doesn't have to be polynomials. If the denominator function goes to infinity faster than the numerator function, then that means this limit will be 0. If the situation is reversed and the higher power function is on the top, then that means the limit's going to infinity. And if they're both approaching infinity at roughly the same speed, because they have the same degree, then it could be approaching a number. Okay, so a little bit more about that later on. Last case we haven't talked about is, let's go back to the limit as x approaches a number, in this case 3. And let's say that maybe this is the initial value, or maybe you've factored and this is what you're trying to plug in, and you're plugging in here and you still have a 0 in the denominator. So after you've done everything you can to cancel out the 0 in the denominator, it doesn't work. You still are going to get divided by 0. And that means you are approaching a vertical asymptote, right? As you get close to the value where you're about to divide by 0, the function has what we call a vertical asymptote, which means the function is doing something like that. And therefore it's going off to an infinity. Since we're not specifying a direction here, we have to just declare that that limit does not exist. All right, I know it's a lot to take in, but kind of refer to that as you work problems to practice. Okay, let's do a couple more things that you might need to do as far as simplifying. We're going to put the majority of these ideas in this section here into this video, and we'll do a shorter following video. Okay, so sometimes if you have this function here, which we had this in the last video, and we did this with a table. We just plugged in numbers getting close to 0.999, and then 1.1, 1.01, and so on. We figured out what this was doing. But let's say we want to plug the 1 in and analyze this analytically. That would give me a 0 on the bottom and a 0 on the top. So I have this 0 over 0 thing. Okay? And by the way, you should not ever write this. Don't write equals 0 over 0. Because this is a currently undefined expression, and we don't want to assert that the limit is equal to that. So we're not going to write this like that. If you want to, off on the side, you can, while you're figuring things out, write 0 over 0. But that should clearly be what we call side work, right? And not connected to the limit. Okay. So instead, what I would do is just say, all right, can I somehow factor this? Can I factor this denominator, hoping to be able to factor out something so that the x minus 1 gets canceled out? Right, well, one way to do that is division. So let me show you an example of division. We can do polynomial division or we can do synthetic division. So polynomial division is, let's flip this upside down and do this division problem. X cubed minus 1 over x minus 1. I'm going to divide x minus 1 into x cubed minus 1, but I'm going to write that as plus 0x squared plus 0x minus 1. So put placeholders for any missing terms in the polynomial. And the way polynomial division works is you take this initial x and say, what would I have to multiply to exactly equal this x cubed? And that would be an x squared. So in the x squared column, I'll put an x squared up here. And then I'll multiply this times this and write the result here. So x squared times x is x cubed. X squared times negative 1 is negative 1x squared. And then I'll subtract this from this. So this has been designed to cancel. 0 minus negative is positive x squared. And I'll bring down the next thing here, plus 0x. Now, what would x have to multiply by to get x squared? That would be a single x. So I'll put plus x here. X times x is x squared. X times negative 1 is negative x. We'll subtract the 2. That's 0 minus negative 1 is positive x minus 1. X minus 1 has to be multiplied by positive 1 to get x minus 1. And that gives me a remainder of 0. And that means that this divided evenly, which means that you can say that this times this is equal to the original denominator here, x cubed minus 1. So now I can state that this limit is equal to the limit as x approaches 1 of, I'm going to factor this denominator. This is this times this. So it's x minus 1 times x squared plus x plus 1. And the top is x minus 1 times a 1. That will allow me to factor and cancel out this x minus 1. So this is algebraically equivalent. The limit as x approaches 1 of 1 over x squared plus x plus 1. And that means now I can plug in the x. This is 1 over 1 squared plus 1 or 1/3. One more note about formatting. On the AP exam, you're not required to simplify, so you can leave this as the answer. In fact, we prefer that you do that in our classes, although you're welcome to, you should be able to simplify if you have to, like maybe it's on a multiple choice test and you have to get their form, which would be simplified. All right, so that's how you can use polynomial division to essentially factor things that are larger than square or quadratic polynomials. And then there's another procedure called synthetic division that does this even more quickly. You can say what number would make that 0 and write that on the side, and then put an L-shaped bracket, and then write the polynomials here, 1, 0, 0, negative 1, the coefficients only, 1, 0, 0, negative 1. And then the way you do this is you prime the pump by bringing this 1 down, and then the idea is you multiply the outside numbers and write the result here, and then you add the column. Multiply the outside numbers and write the result there and add the column. Multiply the outside numbers, this 1 times that 1, write the number here and add the column. This is the remainder out here. This is the 1's place, that's the x place, and that's the x squared place. So that's a much faster way to get this thing that is divided out. All right, so you could use, if it's not easy to do regular factoring, you don't have a quadratic, you can try polynomial or synthetic division to aid in that. All right, a second example in the packet for today includes radicals. So here's another algebraic simplifying technique that you can use. If you're finding a limit as x approaches 9, first try plugging in, but the square root of 9 is 3. 3 minus 3 is 0, so we're about to divide by 0. So we have to do something, but I can't factor this because there's a radical. Can't factor radicals, not easily anyway. So instead, what we can do is whichever side has the radical, we're going to do what's called a conjugate of that. And the conjugate means to take the same pattern, the square root of x and 3, but change the sign in the middle. So if that's a minus, this becomes a plus. And we're going to multiply both the top and the bottom by that, so that we're really multiplying by 1. Okay, I'm also going to factor the top. Okay, so I'm going to just state that this is, I would show that I'm doing this step. And I would say that's equal to the limit as x approaches 9 of, this is the difference of squares. That's going to be x minus 9 times x plus 9 times the square root of x plus 3. And then when you multiply out this radical, the square root of x times the square root of x is the same as the square root of x being squared, and since those are inverse functions, that just leaves an x. So that times that is x, and we would have a negative square root of 3 for the inside part, a positive square root of 3 for the outside part. So this conjugate always results in cancellation of the middle two terms, and then the last term is a negative 3 times a positive 3, so that's an x minus 9. Right? But that means that it can cancel with this x minus 9 here, and that means that you're just left with this times a 1 when you factor that out, x 9, and that means there's no fraction anymore. So this is just x plus 9 square root of x plus 3. And now I can successfully plug in. So I'll drop the limit. This is 9 plus 9 square root of 9 plus 3. You're welcome to leave that as the answer, or you can say this is 8 times, let's see, that is going to be, no, 18, and then times 6, which I think is 108, if I remember right. Let's see, is that right? 18 times 6, yeah, 108. Right, so the answer could be any of those forms. It does not require simplifying. Right, so the key here is if you have a radical, try multiplying top and bottom by the conjugate of whatever side that radical appears. It will move the radical to the other side, and frequently it will result in something that will allow cancellation. All right, that is where we're going to stop the first video for this topic. We'll split the rest of this lesson off into a separate video.